This is the next video in the chapter on advanced theories of bonding. We are going to talk about how valence bond theory talks about multiple bonds. So we learned all about sigma bonds and hybridization in the previous videos. And now you're probably asking yourself, what do we do with the unblended p orbitals? The ones that were left over that we didn't use to make hybrids. So sometimes these p orbitals remain empty, but most of the time we use these to make pi bonds. So remember when we talked about pi bonds, the pi bond was defined by where the orbital overlap happened. So in a pi bond, orbital overlap occurs on opposite sides of the internuclear axis. So above and below the axis in one dimension or another, whereas the sigma bond, the overlap occurred on the internuclear axis. So let's take a look at those energy diagrams that we drew last time, where we showed the energy of the hybrid orbitals. We had our sp3 we had our sp2, which had one p orbital left over. And we had our sp, which had two p orbitals left over. So we talked last time about how we do hybridization. We make these hybrid orbitals so we can use them for sigma bonds, because they all have some S quality in them, and the S quality is the best for forming single sigma bonds. But in a couple of these cases, we have orbitals left over. In the sp2 hybridization case, we have one p orbital left over. And in the sp hybridization case, we have two p orbitals left over. And so these can be used to form pi bonds. So let's look at some more examples of these two types of hybridization specifically, the ones that had p orbitals available. So we'll start with sp2 hybridization. Here's a molecule that experiences this, C2H4. So when we draw the Lewis structure, we draw a double bond between the carbon. Usually we draw the hydrogens in the plane of the page, but today we're going to draw them on an angle. We're going to look at the molecule from a slight angle, to emphasize the geometry. And so we learned how to count sigma and pi bonds before. We said that the first bond made between any two atoms was always a sigma bond, because that was the strongest. So there's 1, 2, 3, 4, 5 sigma bonds in this molecule. And any additional bonds, more than one, those were all pi bonds. So there's one pi bond between this carbon and the other carbon. So let's try and picture what that overlap looks like. We'll just go ahead and start by drawing the sigma overlap, just as a review. And we're going to use dots in place of the atoms. So for sigma bonding, we'll do the hydrogens first. Each of the hydrogens only has one orbital to use. It only has a 1s orbital. And then we'll use two different colors for the carbons, a red one for the left one and green for the right one. And so these carbons are sp3 hybridized. Sorry, sp2 hybridized, because they're bonded to three things. And so they're going to have three sp2 hybrid orbitals that they use for those overlaps. And the same thing is true for this carbon. It has three electron groups, so it's going to form sp2 hybridization. There's going to be one sp2 hybrid orbital for each of these overlaps. And so there we can see our 1, 2, 3, 4, 5 sigma bonds in those overlaps. So now let's draw the picture again, where we have a little bit more space so it doesn't get too crowded. And let's show the p orbitals participating in the pi bond. So the hydrogens don't have pi bonds, so we don't need to draw anything for them. And we know for sp2 hybridization, each of those carbons has one p orbital available. So there's a 2py orbital on this carbon. And there's a 2py orbital on this carbon. And so that forms our pi bond. And these form our sigma bonds. There's one pi bond that occurs in an sp2 hybridized molecule. So let's look at sp hybridization now. So a good example molecule to use is C2H2. The structure looks like this. Single bonds between the carbons and the hydrogens, and a triple bond between the two carbons. We know that the first bond between every pair of atoms is a sigma bond. So there's a sigma bond here, a sigma bond here, and a sigma bond here. So three sigma bonds, and all the multiple bonds, all the additional bonds will be pi bonds. So there's two additional bonds here. So there's going to be a sigma, a pi, and another pi bond in between those two carbons. So there's going to be two pi bonds in this case. So let's draw the orbital overlap for this picture. So again, the hydrogens only have one orbital to use. Their 1s orbital. The carbon, each of the carbons is bonded to two electron groups. So it's going to be sp hybridized. So each carbon is going to have two sp orbitals, which should be the same size, even if your picture doesn't look the best. And the other carbon is sp hybridized as well. So it has two sp orbitals that it uses to form bonds. So hydrogens have used their one valence orbital. Carbons have each used two. They have two left. So now we'll draw the pi bonds. Hydrogens don't participate in any of the pi bonds. The carbons do, and there are going to be two different pi bonds between the same atom. So we've already used the x-axis here. So the first set of pi bonds is going to be along the y-axis, and the other set of pi bonds is going to be along the z-axis. So watch how this works. Here is carbon 2p orbital on the y-axis. And on the other carbon, the 2p orbital on the y-axis. So these overlap to form the first pi bond. And then we have a similar shaped overlap, just on a different axis. The one that's the hardest to draw, we'll try. So it kind of looks like this, sticking out into the page. So this 2p orbital is on the z-axis. And this carbon also has a 2p orbital on the z-axis. So the overlap of these 2p orbitals on the same axis forms a pi bond. The overlap of the other two carbon p orbitals on the y-axis forms this pi bond. And then we have 1, 2, 3 sigma bonds. So 3 sigma bonds and 2 pi bonds here, 5 sigma bonds and 1 pi bond here. The important part is that the pi bonds are going to be overlaps of p orbitals, and each additional pi bond overlaps on a separate axis. And those overlaps are on opposite sides of the internuclear axis. There is no density here on the internuclear axis in a pi bond. In the next video, we will talk about how to use what we now know about p orbital overlap and pi bonds to understand resonance a little bit more.